Hi there everyone and welcome back. So today we are taking a look on page 23 of quadratic modeling of volume. So let's just take a look on the first exercise. So we're going to write a function of degree 5. Okay, so it's of degree 5. It has these zeros and it's tangent to the x-axis at 1. Okay, well, hopefully you guys remember. See how I have a 4i here? So really I'll just write this out. We have x equals -2, x equals 1, and x equals 4i. This comes as a conjugate pair, so really it's plus and minus 4i, okay? And there's another piece of information. Again, that's the reason why the plus or minus, because of conjugate pairs of imaginary solutions. And it's tangent to the x-axis at 1. So I'm going to make a sketch. So those are my roots. So that means I've got to have a multiplicity somewhere, right? Because this is to the 5th degree. So right now I only count that's appearing right now once. That's appearing right now once. And then we have two imaginary roots. Okay. Well, we know we have a root at -2 and +1. And it's to the 5th degree. So its end behavior is either going to be down, up, or up, down. Okay, it could be either or. Remember, it says write a function. So we could have a leading coefficient that's either negative or a leading coefficient that's either positive. It doesn't matter, okay? It says write any kind of function. So I'm going to go with a positive leading coefficient, right? We're going to write a function. So right now I have y equals, I have one of my factors is x plus 2 because the root was -2. I have x minus 1 because the root was +1. And then we'll have x minus 4i and x plus 4i. So x plus 4i. So let me actually rewrite this, make this neater. Now, in terms of my x minus 4i here and x plus 4i, I actually know, oops, I didn't mean to get rid of that. Okay, if I have x minus 4i and x plus 4i, if you were to redistribute this, you'd end up getting x squared plus 16, which should make sense because this is not not dots. Okay, that's hence the imaginary roots. So I'm going to write this is x squared plus 16 for those imaginary roots of plus or minus 4i. And now we want to come up with the next piece of actually sketching this. So it's tangent to the x-axis at 1. Well, that tells me we've got some kind of multiplicity going on here, right? That's tangent right now. That's tangent to the point 1 of the curve. So if we assume a positive leading coefficient, remember we could have done negative, so we're going to assume the leading coefficient is positive because it says write any function, right? Any function, as long as it follows these characteristics. So we're going to start coming from down. If we're assuming a positive leading coefficient, we have down, up, and behavior. So we're coming from -2, hit a y-intercept wherever that may be, and then continue my graph. Okay, where we have imaginary roots. Okay, definitely draw a better picture than me here. So that's what my graph could look like. And you guys could simplify this, right? I'm not going to go through the algebra here, but this is an example of an equation that you could see. And we would want to write x minus 2 squared because of the multiplicity. Okay. All right, let's take a look at the next example. Okay, and I'm actually going to skip to exercise 3. So let's take a look at exercise 3. We have an open box. Okay, so it was a box, hence the 3 dimension. We're in volume. It's made from a square piece of material, 24 centimeters on a side, by cutting squares of equal length, x, from the corners and then turning up the sides. Okay, so I'm going to sketch a picture here. So here is my square, and we're cutting the corners, right? We're cutting the corners of a length x. So if I cut out the corners, right, because then we would be able to fold this box. Okay, so that's of length x on either side, right? All of those are of length x. Okay. All right, I'm going to just draw another picture, maybe make this a little bit more clear if this isn't already. Okay, so I just showed that the edges are cut out, so maybe this picture is a little bit more clear, this one. Okay, and we know that the whole length, before I cut out those pieces, the whole length on each side was 24 centimeters. So if we're cutting out, we cut out x here, and we cut out x here, I know this length is going to be the difference of 24 and these two x's. So this length here is going to be 24 minus 2x. And that's going to be the case for all of these now new lengths here. That's going to be 24 minus 2x all the way around. Okay, I'm just not going to write it for all of them. Okay, well, the question says write an equation for the volume. Write the equation for the volume. So if we were to fold this box, I understand this is probably a little bit hard to picture, but if we were to fold the pieces up, okay, we would be looking at something in 3 dimensions. Okay? I'm trying to draw my best here. Okay, so we'd be looking at something in 3 dimensions. So this would have that length of 24 minus 2x. This would have a height of x, right? Volume is length times width times height. So we have a length. We have a width, right? Length times width, which is also that 24 minus 2x, and a height of x. So we're multiplying all 4 of these things. So that's our equation. Our volume, write it as v of x, that's what it told us to use, is going to be 24 minus 2x times 24 minus 2x times x. Length times width times height. Okay. The question now we want to take a look at is to come up with the domain. So let's come up with the domain for this box. Well, let's see. Domain pertains to the x values. All right. So I know that this thing can't have a negative length, right? We're talking about domain being the length for the corners. Okay, if we're talking about x being the length of the corners. So we're trying to figure out, well, what are the dimensions, what length measure could the corners have for this x value? Well, we know that the smallest value is going to be 0, but we're not going to include 0, right? Because if I have a length of 0, then there's no box, okay? So we want to figure out what's going to be the largest that x can be. Well, take a look at our function, right? We just said the smallest that x could be is as close as possible to 0, but we can't equal 0 because if we equal 0, I've got no length. Okay, so let's take a look. Let's set one of these roots equal to 0, right? These are all factors. So I have 24 minus 2x. Let's set that equal to 0. Bring over the 2x, because again, we're dealing with domain. Domain is our x values. And I get x to be 12. So we could be between 0 and 12. We can't equal 12, so this is important. You cannot equal 12 because if I take a look, what happens if x is 12? Well, if x is 12, I'll just write it here just so you guys can see. If x is 12, I'll have 24 minus 2 times 12, and I'll end up having 24 minus 24, which is 0. And I'll have 0 times this entire equation, so that's no good. Okay, so we're between 0 and 12. And I'm going to show you guys this on the calculator. All right, so as you guys can see, I have my equation typed in to y equals. Just to remind you guys, to get to y equals, we hit that diamond F1. Okay, we hit diamond F1. So I already have my equation typed in. Okay, that was from here. That's just my equation. I didn't simplify it. I just left it as it is. And now I want to graph this. So I'm going to click diamond F3. Now we're going to want to adjust the window because I don't like how I really don't see anything. I don't see anything. So let's adjust the window. If I hit diamond F2, well, our minimum x value, right? This is our domain. So my minimum x value should be 0. So let's type in 0. X max, we can make it go to 20. Doesn't matter. We can go to 15 if you want. Y min, we can leave it at -10, sure. And Y max, I'm going to want to make this huge. Okay, we're talking about volume. So maybe I'll make it like 1500. Okay, and click enter. I'm going to graph this now, so I'm going to hit diamond F3. And there you have it. There is my cubic function. Okay, there is my cubic function. Notice how it kisses the graph here. Okay, it's kissing the graph here. So we have a multiplicity of 2, and there is a root here as well. So this should make sense that this is a cubic. It's got 3 roots. All right. All right, so you just saw our graph, and now the question says determine the value of x that's going to produce the maximum value. We want the max value. So I'm going to go back to the graph here. All right, so if I come back to my graph, you guys can see here's where my maximum exists. Okay, it's right there. Sorry, my hand is a little shaky because I'm trying to hold the iPad as well. So there is my maximum. So to get the max, I'm going to go to F5. You're going to scroll down to where you see maximum. It's a relative max. And where it says lower bound, I'm going to move left of the maximum. So I'm moving my cursor all the way left of the maximum. I'm going to click enter, and then I'm going to move right of the maximum. And I'm going to click enter. And there you guys see. My maximum is when x equals 4. So let me just circle that here. When x equals 4 and y is at 1024. So those are our maximum values. So we kind of just answered parts C and D. It says determine the value for x, which will produce a maximum, and determine the maximum volume. So there we go. That's it. So I'm going to write when x equals 4, our max value for the volume is when y equals 1024 centimeters cubed. Alrighty. So hopefully this was clear on how we came up with all these values. Okay, let's take a look on the next page. Let's take a look at exercise 4, and we're also going to do 5, 4 and 5. So for exercise 4, I drew a nice picture here for you. Very beautiful. We have an open top box is to be constructed by cutting out the squares. So again, we're cutting out the squares on each corner. So we're cutting these out, kind of like the picture I drew before. And what else do we got? This cut out from the squares from each corner of a 14 by 20 sheet of plastic. So this looks like the longer side to me. So we're going to call this length 20 and this length 14. And they each have that side length from the corners as W. So these are all W. So again, kind of like before with that last setup, we wanted to come up with what these lengths were, right? What were these lengths? Okay, because eventually we're going to want to fold this, right? We would fold this box so that it has an open top. So if we were to fold this again, kind of like the picture I drew before, this is what it's going to eventually look like. Don't mind my drawing skills. Okay, so that's what my box would look like. So this has that length of W, and we have this length here, and this length here. That's what these pieces are. I'm trying to color code them so you guys can see that. Okay, well, we know this is 20 minus 2W because it has the W on either side that's getting cut out. So this is 20 minus 2W. And then from here to here, well, if this whole length is 14 and we're taking out W on either side, then this will be 14 minus 2W. And now we're looking at the same setup, very similar to what we just did before. All right. Remember, volume is equal to our length times width times height. So I'm going to multiply all these things. I've got W times 14 minus 2W times 20 minus 2w. Notice I didn't simplify anything, all right? That actually makes it way more work for us. And again, you guys can graph this, see what the graph looks like, and come up with a domain. So we want to talk about what the domain would be. We want to talk about what's the max volume. Okay, so what's the max volume when x equals what? Or sorry, really I should say w. So when w is equal to what value will we get our max volume? So we want to figure out those two pieces. Okay, so let's graph this so we can check out the domain. Okay, and that looks pretty clear, zoomed in, awesome. Okay, so I have the equation typed in, so we're using x times 14 minus 2x times 20 minus 2x, okay? I know we used w's here, okay, I know we used w's here, but we want to make sure we're using x for our y equals on the equation. I'm then going to go over to graph it, so we're hitting diamond F3 to graph. Okay, diamond F3 to graph. Now you'll notice the whole graph doesn't fit. So we need to adjust our window. So I'm going to adjust my window by going to F2. I'm sorry, diamond F2, I apologize. Diamond F2. Well, we can't have negative x values, right? We want them to all be positive. So we'll make that go from 0 to 10. And let's see, maybe even like 0 to 15, right? We can make it go longer. We already know if we were to t-chart here, right? Okay, if we were to have t-charted, we would have found w to equal 0. We have 14 minus 2w to equal 0. And then 20 minus 2w equals 0. When we solve for w here, I'll get w to be 7. And then w equals 10. So these are the x values that we're going to be looking at. So, I mean, I'm making mine go to 15 just so I can see more of the graph. And now let's go back to diamond F3. I'm going to have to adjust the y values. Okay, so there we go. Now I can see more of the graph. That's good. But I need to adjust the y values. So if we go back to diamond F2, yes, that will adjust the window. But let's check the table, right? You guys can see, look at my table. My y values are pretty large there. We're going up to like the 300s. So maybe I'll make my y max 350. So maybe I'll make y max 350. Okay. And we'll go back to diamond F3. There we go. Now I can see the curve. Okay. And guys, remember when we're talking about this, right? These values here, okay, these values, they have to be positive if we're talking about this graph, right? So over here, if I actually were to adjust my window again, just to give you guys more of the graph to look at, okay, so maybe I'll make that go to negative 100. We can't have negative y values, but if you look, it does fall into that category of negative y values. Okay, so this part of the graph doesn't make any sense for us, right? We're trying to talk about cutting out corners from a open top of a box, given the dimensions we're going to side it. You can't have negative dimensions. So even though this goes from 0, that's the 0.7, and here is the 0.10, we actually don't include the domain from 7 to 10. Because again, if you just look at the graph, you have negative values for x. That doesn't make any sense. So our actual domain is from 0 to 7. Okay, our actual domain, try to trace over it, is from 0 to 7. We're not looking at them greater than 10, because if they're greater than 10, well, look what happens. Let's say if w was 11. 20 minus 2 times 11, we have 20 minus 22. You can't have a negative length. Okay, so this piece over here, I'll write it in blue. We don't count this. You can't be greater than 10. We have to be between 0 and 7. So that actually helps us with the domain. We know the domain is between 0, or I should use w. Sorry, we're using w. Okay, so my domain is really between 0 and 7. Okay, because again, if you looked at the graph, you would see how it dips down, which we don't want. Okay, and lastly, we want to find the max volume as well as the value for w, which in our case we're using as x. So here's the maximum right here. So to find the max, we're going to go over to F5, scroll down to maximum. we're going to move all the way to the left, so I really got to move my cursor. Lower bound means move to the left of the maximum, and we'll click enter. So move left of the maximum, click enter. Upper bound means move right of the maximum, and then click enter. And there we have it. There's our max X value and our max Y value. So find the original dimensions of the box. That's what the question asks. Find the original dimensions. Well, we can just use our equation here. Just plug into the equation here. So we have W, and how do I want to round this? Let's round this to the nearest hundredth. Sure, we'll round to the nearest hundredth. So we'll have W is equal to 2.70. And we just want to evaluate what these pieces are. What's this and what's this? So we have W is equal to 2.70 centimeters. Let's see, that 20 minus 2W is equal to, again, if I just go back to my home screen, we're using 2.70 for W. So minus 2 times 2.70. We have one of the other dimensions is 14.60 centimeters. And then we'll just look over here, plugging in again. And here, let me move this video. We don't need that. Okay, so just plugging in again. We have 14 minus 2W. And again, I'm just typing this into my calculator. Times 2.70. Okay, so obviously you guys are seeing that we're using a calculator for these questions. And those are the dimensions, okay? These are the dimensions. I really should just be highlighting here. These are the dimensions for the open top of the box. And if we wanted to just find the maximum volume, okay, we actually already found that from the graph. Okay, so we found that from the graph. Our Y value was 339.01 centimeters cubed, which you can also find just by multiplying these three values. Okay, hopefully this helps, guys, with identifying all these pieces. There's a lot going on. Okay, last question. We're going to take a look at exercise 5. We have Dixie Packaging Company has contracted to make boxes with a volume of approximately, we have 484 inches cubed. Okay, so we're dealing with a volume, which is inches cubed. Squares are going to be cut. Okay, so that's nice. So equal length on either side. Squares are going to be cut from these corners, so hence these corners are being cut. Sorry, this got a little cut off here. Okay, so these corners are being cut out, and they all have that uniform width. So I'm just drawing in all these values have a length of X. And we know that from each corner to make the open box, so we have from here to here is of length 25, which is given to us. And then from here to here is of length 20. Okay, so this is similar to the problem we just did before. And the question asks what size square should be cut from the cardboard. Okay, so we can recreate our picture. So we know if this whole length is that 20, and this is X and this is X, we know this length to be 20 minus 2X, right? We just did this in that previous problem. If this whole length is 25, and we have X's on either side, right? And we're cutting this piece out and this piece out, to get this piece, we know that that's 25 minus 2x. And if we were to just, again, recreate our three-dimensional rectangular box, okay, so if we recreate our rectangular box, looks something like this. Okay, we know this has a dimension length of 25 minus 2x. This has a dimension length of 20 minus 2x, and we have this height is x. So again, with our formula for volume, right, volume is length times width times height. We have 25 minus 2x times 20 minus 2x times x. And again, we want to graph this, okay, because we're going to try to find out what. Let's go back to the problem. Okay, we have the volume. Okay, they're actually giving you the volume, guys. They're giving you the volume. So we just want to know what values for x were cut to make that volume. So let's graph this. I give you the volume. The volume is already 484 inches cubed, right? So if this volume formula is y equals, right? This is really y equals, and so is this. We're going to graph two y equals equations. This is one, and this is the other one. Okay, so let's graph that in the calculator. Okay, so I typed both of my equations into y equals here. Right, so both of my equations are typed into y equals. Okay, so here and here. And now we're going to graph it. Now, before we graph it, I am going to look at the table to make sure that diamond F5, to make sure that I have the appropriate window. And if I look, I'm going up to some pretty high numbers here, guys. So maybe I should make my y max, I don't know, let's make it like 900. See how we go up to 816 there. So if I go back to diamond F2, okay, I'll make my y max about 900 and go back to diamond F3 to graph. Okay, now I just do want to talk about domain as this is getting graphed. Remember, the domain x values we can find by finding the roots. Okay, find the roots. So if I have 25 minus 2x equaling 0, I have 20 minus 2x equaling 0, and x equaling 0. So we know we're going to be between 0 and what? Well, remember, we don't include, oops, not there. Sorry. We don't include these negative values. That's dealing with a negative area. You can't deal with the negative area. So your domain is going to be from 0 to whatever this x value is here. Okay, so it's going to be the smaller x value of the two. So let's do that. Okay, so I'm just writing this out here. Add my 2x to both sides. I have 25 equals 2x. We get x to equal 12 and a half. So that is actually this value right here. This value right here is 12 and a half. And over here, right, add the 2x to both sides. We get 20 equals 2x. So x has to equal 10, which is this point right here. So our domain is between 0 and 10. 0 and 10. That's for our domain. Again, we don't include from here to here because there's a negative area, which doesn't make any sense. All right, and then guys, just the last piece that we have to do is just find these intersection points. Okay, we want to find where these intersect because the question is specifically telling you that we want the volume to be 484 inches cubed. That's why that was one of our values that we graphed here in y equals. Okay, one of the values that we graphed was y equals 484. So we want to find where those points intersect. So if I go over to F5, scroll down to intersection and click enter. Okay, I'm on the first curve, which is the cubic polynomial. Click enter. Second curve, click enter. Now it says lower bound, so I want to move left of the intersection point, which is right there. So move left and then move right. Click enter. And there we have it. There's one of the intersection points. So look, there's that volume at 484, and here's one of the potential values for x. So x can potentially be 6.87147, and let's check what the other x value is. Okay, so again, go back to F5, go to intersection. We're moving all the way over because we want to get to this intersection point here. This intersection point here. Okay, so I just got to move this cursor all the way over. First curve. Okay, I'm on the second curve, so let me just erase. Okay, let's erase. We're looking at this point now. Click enter. Lower bound, move left. Upper bound, move right. Enter. And here's my other x value when x equals 1.22232. So these are the possible x values to make this cut up cardboard box. Okay, and here you guys have it. These are the dimensions. These are actually, you have options. The dimensions for this cardboard cutout box could either be these dimensions. I didn't round anything because the question didn't say to round. So I could have either these dimensions or these dimensions. Okay, you actually have options for either one of these will get you to a volume for the box of 484 inches cubed. All right, guys, I hope you found this video helpful. Again, I just found these numbers by literally plugging x in to this equation here. I'll talk to you soon.